Stressed faults and normal faults can be added as 3D surfaces to a geological model, matching geological outcrop data and 2D geological cross-sections. The way I add fault planes to a 3D geological model is summarized in this slide, and we will go through it now with two examples. Here we see a cross-section and the intersection of the thrust fault with the surface. The model is explained in detail in a separate video you can access with below link. In our model, the thrust fault is not a simple flat surface, but has been also deformed and folded. I will now place the pointer where the thrust fault intersects the 2D cross-section at surface. The transformation pivot point is set to bounding box center. In object mode, add a plane, scale it up, and add the texture property blue. We will start constructing the thrust in the west and use as a guide the 2D cross-section and the surface geological data. The plane is currently in horizontal position and east-west aligned, and I will rotate it according to outcrop measurements and geological mapping into its local strike position, and move the plane then into the western part. I place the cursor at the intersection of the thrust with the cross-section at the surface again, and change the transformation pivot point now to 3D cursor. Then I rotate the plane until it matches the thrust plane actually mapped at the surface and according to the construction of the cross-section. In edit mode and transformation pivot point set back to boundary box center, continue matching the thrust according to the 2D profile construction. I add additional edges using loop cut, press Command R as required. If the thrust plane needs extension, select the edges at the end of the plane and extrude region by press Command E and extend the plane along the x-axis. After the cross-section is matched, I continue with loop cut and extrude region until the thrust plane conforms with the geological map and the geological model. Here my final result of the 3D thrust construction, the result of several iteration and editing. Let's construct now a normal fault that dips 60 degrees to the horizontal and that terminates at the thrust plane. Transform pivot point is set to the 3D cursor. The cursor is placed at the northern endpoint of the normal fault so that rotation and scaling is done with reference to that cursor position. I rotate the plane 60 degrees to the horizontal and switch via View, Viewpoint Top or shortcut numpad 7 into top view to rotate the normal fold roughly along the outcrop trace. In edit mode, I add and use edges to match the outcrop trace. For this, the transform pivot point is set to bounding box center. The thrust fold and the normal fold are now constructed in 3D and shown here in relation to the 2D cross-section and the geological map. We have constructed a normal fold in red, which terminates at the thrust fold, shown in blue. Moreover, we have the intersection of these planes with the surface. In red the normal fold outcrop and in blue the surface trace of the thrust plane. The normal fold currently cuts through the thrust plane, but we need to cut the normal fold along the thrust plane. This we do via the Boolean modifier, the procedures captured on this slide. Two steps are needed. First, we make copies of each plane. Secondly, we cut the normal fold along the thrust fold. Step 1, we make copies of the two planes to work with to safeguard the full construction in case something goes wrong with the Boolean modifier. Exclude the original planes from selection and hide. Then we use the Boolean modifier to cut the normal fold along the thrust fold. Here we see the final model of the thrust fold and the normal fold. Of course, this has not been constructed in isolation, but simultaneous with the construction of the deformation of the overthrusted thrust sheet. This leads to the tutorial part 4, where I will show how true 3D fold construction can be done in blended GIS to arrive at the model like you can view in the following clip sequence. I hope you find the tutorial useful.